All right, so Tarika seems to be having problems connecting. All right. There we go. All right, so what we're doing, I mean, we're going to walk through the syllabus still. No, let's go back to the syllabus here. Again, I don't know if everybody understand how to read the syllabus, but my job is to break it down for you. In fact, what I probably should do is just take out each of these objectives and put them on a side by themselves, and then afterwards we go through them individually. So write the formula to represent ions, molecules, and formula units. All right, now let me see something. Yep, write the formula to do that. Why is this not going up? Let's just get it up here. Good.
Sir, I'm going to rejoin.
You wanna rejoin? All right, fine. All right, so Tarika, you can hear me? Okay. And all right, and let's get this here. Explain metallic bonding. And just taking this right out of the syllabus. These are like questions that they could ask, just as is. And see CXE questions, and actually we're making our own CXE questions, right? Just like how people can make their own fried chicken at home. So we can make our own CXE questions in class. And just picking out what the syllabus says that we should cover. And when you do it that way, and you ask, all right, and I ask like if anybody should ask what will be coming an exam, just point it to these questions. These are coming an exam. What has come before has been these. What will come after will be the same thing like this. Now, remember guys, when you're doing exams, especially CXE exams, these persons are lazy when they write questions. They don't want to have to write a question over and over. So what they do, when they get it right one time, they just change the words minimally and probably put in a diagram the next time, find other ways to ask the one question. So let's just say, for example, we're seeing this question here, explain metallic bonding. Okay, fine. So they ask it like that this year. Next year, that question will probably turn up with a metal, and they ask you how does that metal, how is that metal able to conduct electricity? And then you're scratching your head and saying, well, we'll never learn this. But fine, you learned about metallic bonding, and that's the answer. If you can explain metallic bonding, you can explain how metals conduct electricity. All right? I hope you're understanding what I'm saying to you guys. All right? Questions will not always be direct.
Sir, and metallic bonding is the bond between two metals.
No, it's not the bond between two metals. And so it's a good reason why we do it this way, because metallic bonding is bonding within metals, not between metals, but within metals.
Okay, so what's the difference?
Yeah, well, between metals will suggest that the two of them react chemically, and two metals cannot bond chemically. All
Okay.
right. Yeah. Yeah. So two chemicals cannot bond. chemically. So it'll come in like this. All right, you see like what I'm showing you now on the screen like this?
Yes, sir.
Yeah, all right. Imagine that. Can these connect together this way?
No, sir.
No, that's how it is. So this is a metal, this is a metal, and the two of them can combine like that, right? However, look at this now. So that this is a metal, right? And this is a metal, and then this is a non-metal, and they connect. You see that?
Yes, sir.
Yeah, the same thing. So metal and metals. However, here is the catch now. Two non-metals can bond, and in that case, it's a chemical bond, but it's called a covalent bond. So that I think that's what might be, you might think in your head, say, well, then if two non-metals form a covalent bond, then you're thinking that, well, two metals would form some sort of chemical bond, but that's not true. The bonding between metals, it's actually it's within between metals is always physical. That's the rule there. So if two metals combine together, they don't react chemically. And when we say chemically, we mean that no transfer of electrons don't take place, or no sharing of electrons take place, right? What happens with metallic bonding is that within the metal itself, there is movement of electrons from one atom to another, but it's a temporary thing. And it's temporary in a way that because electrons are always moving, it'll come in like a tree that hung over. Like it's in your hole, it's in your yard, but it hung over the neighbor yard. Right? I don't know if anybody can relate to that. Anybody have any tree that hung over in the neighbor yard?
Yes, sir.
Yeah. All right. So what happens if it's a mango tree then and mango season come and then the part that hung over the neighbor house, do they take that mango for themselves or then give it to you when it drop over? How it work?
Well, sir, it's the other way around. They have this like pumpkin vine that comes across the fence over our side. So
Yeah.
usually when it grows, mommy would take it.
Mhm. Hold on, let me see. So the vine start over the other person over your neighbor house
Yes.
and it come over into your house.
Yes, sir.
And then when it bear, you take it.
Mommy takes it.
No, but you say your mother, you wanna eat it too? So you
Yes,
take it.
sir.
Yeah, so you tell your mother take it, you take it too. All right, but it's the same thing. All right, with metallic bonding now, and you're going to do a familiar diagram for you guys to understand metallic bonding. All right, let's go to the image and show you this one. This is and I believe I'll show you already. I don't know if I didn't. Well, let's refresh your brain if I did. Okay, so this is a nice one, and okay. Let me create some space on this so I can paste it. All right, let's scrap this, make it smaller. And this is our metallic band. This is our metallic band, guys. One sec, I never crap one. Yeah. And it's small this up and in zoom it in. So that's what it is. Electrostatic bond between electrons and metal ions, but then these ions now are created within the metal itself. So let me see if there's another way to show it. And when we say metal ions now, in this case, what you're seeing here is like in a metal, and this is coming from metals. So, and let me show you what metals mean in chemistry. Metals mean anything on the left hand side of the periodic table. So Yeah, I want to show you what that looks like. Most of the periodic table are metals. All right, let's find one that may be easier to understand. And here it is. You know, this is, you have to learn chemistry very in an organized way. All right, everybody seeing this?
Yes, sir.
All right. So metals now, guys, as I said, towards the left-hand side of the periodic table, everything over the left-hand side that you see in red are metals. Look at that. That's most of the periodic table. All right. So, but all metals go through metallic bonding. And so that's why the syllabus asks us now to explain what is meant by metallic bonding. Because, well, one, they expect you to know all the metals in the periodic table. And then what goes for one metal goes for all. All right. So that's how it works. Now, okay, so here's another one. Well, this one, however, is and there's another image here to show more of the metallic bonding. So if I show you this image here, right, but you seeing this?
Yes, sir.
Now, what is it? What is it that you're seeing? What does this look like? Right. So
Okay, the valence electrons from the outer shell
no,
are
not talking about that. I'm talking about the circles and what do the circles represent? The circles and the dots. What do the black dots represent? What does the circle that they are on represent?
the circles would be the shell, and then the dust would be the electrons.
Very good. I hope everybody is following this. Vanessa, Terika, and Sachet. All right. So showing the electrons and the shells. All right. As you see, they're obeying the rules that we learned before. 2 on the first shell, and then a maximum of 8 on the second shell. And then the last shell now, you see that V there. That one of the dots. And this is, and you notice that it's not on the last shell, but the shell is still there, but the valence and the V stands for valence electrons, as you were saying, Kimberly, a while ago. Right. So this now, the V, let him call it delocalized valence electrons, right? Delocalized mean that it has been separated. It has been separated from the, and it's a temporary thing though. Right? It has been separated to the from the atom that it belongs to. All right. So it's like a stray. Yeah, like how pumpkin vine run in Kimberly's yard. So the same thing. It's straying. However, well, if you were to so basically this is telling you that electrons in metals are free to move. Electrons in metals can stray from their atoms. And because they can stray from the atoms now, that makes it easy now to conduct electricity, because electricity is the flow of electrons. So what electricity does, and let me show you a diagram here, because this question could come in many forms. Let's give you an example here of magnesium. All right, this is actually showing you how we can produce electricity from metals. All right, and let's look at this image here. All right, everybody seeing this?
Yes, sir.
All right, it's good then. And what's happening here? Magnesium metal conducts electricity because the cations are free to move and carry charge. Yes, cations in the sense that cations are atoms that have lost, whether temporarily or permanently, atoms that have lost electrons. And in this case, so this diagram uses a red circle to represent the electrons. But what this is saying, that 2+ is saying that magnesium has 2 electrons on the outside shell that are free to move. And so the battery is placed there what the battery does, it has something called voltage. And then voltage is like a force. It's, it's like something that's pushing. It's an electric force that you send through materials. And when you send that electric force now, the electrons respond to it by moving, and that's what causes current. When that current passes through, this is like a piece of wire connected to the magnesium, as an example. All right. These electrons move, and they move through the bulb. And when they move through the bulb now, so they go this way and they come out this way and they continue flowing around. Right. So that's how the bulb is able to light up. Right. So that's how electricity is produced from metals, because they have free electrons and they're outside shells. Everybody understand that?
Yes, sir.
Sashi, you understand? Terika? All right. So
Can you repeat, please?
repeat what?
Understood.
I'll send it in the video. Because I said a lot of things before. All right. So, all right. So then that's it. So that's explaining metallic bond. So I'm saying now CXC could set a question from this angle, right? And it's about metallic bonding, as well as they could ask it directly to explain metallic bonding. If they ask you to explain metallic bonding directly, this is what they will be looking for. As a matter of fact, let's go back to that question. In fact, and we'll remove this diagram, because the better diagram to explain that one would be this one here. And let's copy that and put it here. All right. All right, so yeah, I see it takes sachet, which is good. You understand there? All right, there is Kimberly, but then she left. All right, guys, so that's metallic bonding. And metallic bonding, this is example here. All right, so Jonathan is here. All right, so and that's metallic bonding there with the example. So metallic bonding.
Sir, can you explain this, please? My laptop just shut off instead of it running into some errors.
Oh, okay, did you see a blue screen when that happened?
Yes, sir.
Yeah, it means probably a hard drive is filled, or your hard drive is going.
Okay, sir.
Yeah. You have a lot of information on your computer.
Yes, sir.
You're going to have to start you have to start save it. Put it on something else, because if that happens, it means that your hard drive is running out of space.
Yeah, this is actually the second time that happened.
Yeah, and it's going to continue to happen if you don't move some of the information to somewhere else. You can use OneDrive. You can use OneDrive, or what you call it? The Google one, Google Drive.
Yes, sir.
Yeah, so you have to send information to it so that if it goes, and how long you have that, by the way? How long you have that computer?
It was bought in December last year. December? No, I think 2019.
19, okay. It was a new one.
Yes, sir.
Well, you buying it new doesn't mean that the computer is new still. But then the type of hard drive that they're using now, them have actually changed in the last couple of years. So and it should be interesting to see what type of machine it is though. All right. All right. In terms of metallic bonding though, and it's in your textbook, but I don't think I like how the textbook explain it. Because textbook, when people write textbook in the Caribbean, it's like a lot of these persons they either them teach or have taught at some top school, and the language that them use to teach or to write for the kids is a bit high for some schools or some persons. So my job here now is to break it down for you. But anyway, the idea here is to explain metallic bonding, and we use sodium metal as an example. Many sodium atoms are bonded together. However, valence electrons. So valence electrons. All right. Leave the outermost shell. So when you say bonding between metals earlier, Kimberly, you could be correct if you say metal, if it's a bonding between metal atoms. If you say bonding, if you just say metal and stop, then you make it sound like, okay, sodium can combine with magnesium, which is not so. But sodium metal atoms can combine with other sodium metal atoms. The valence electrons leave the outermost shell, right? And they call it delocalize. That's a term here. Electrons leave the outermost shell. Probably should use even a red color for those lines that I just draw. Or some other colors to point out here that the valence electrons leave the outermost shell. All right. And so, and that's it. All right. So, the electron, them, as you say, they come in like, you can imagine like different persons in your family, especially if you have brothers and sisters. The ones who are older tend to spend more time away from the house. Is that true? You're older, spend more time away from your house?
Not for me, sir.
Not for you. Interesting. How about Jonathan? Jonathan, still there?
Yes, sir.
Yeah. Is it true when people older them spend more time away from their house?
Not me, no, sir, because I really want people know me so much.
It was some indoor people, man. I'm telling them, man, for good.
If me like this, like a country or so, sir, would I go out, sir? I go out every day, but today I'm here and I go out, sir. I just don't like the community.
Which community is that?
Melrose.
Melrose? Melrose not bad, man.
They can't chat, though.
No. Yeah, busy people that chat him. Yeah.
Mm-hmm.
Well, as I saying that, well, you wouldn't fit in this category then. But all right, because you probably not reach at the stage in your life, so you can't relate. But when you reach at like 19, 20 now, it's like if you're still there parents' house, you feel like say you want your own space. And so that's how electrons on the outside shell are. The ones that are on the outside, first of all, they have more energy than the ones below it. So any electron in the third shell, like if you're looking in this diagram, you're seeing 1, 2, 3 shells, right? And on the third shell, there is a valence electron that has left or strained outside the atom. Like it wants something else. Like it tired of that like, third shell and want feel some other shell or something. And so this one now, if you look at this side, this one is actually bonded here. It's actually in between the two of them. And so some books call it a sea of electrons because the valence electrons now when them stray, them tend to fill spaces between two atoms. All right. And remember, it's just the valence electrons that do that. All right. Valence electrons, they can well, they cause chemical bonding because they have the most energy available. And anytime two things are bonding, it's dependent on the energy that's there. So it's just like in real life still. You're not going to just talk to anybody. It have to feel right. The energy have to be right there from the person, So so I guess that's why probably Jonathan and Kimberly don't want to leave your house. The energy is not enough outside for you to leave. Jonathan, you're not really afraid, but you're kind of not like when people talk and something, right?
Yes, sir.
You like when people mind their own business and you do what you have to do. Yeah.
Yes, sir.
Yeah. And Kimberly, probably she love her mother so much that she don't want to leave her right now. Is that true?
Yes, sir.
Yeah, that's good. That's good. I'm gonna read them. So, all right, so I'm gonna read up good. All right. Terika, not hearing from you, but I know that when you get bigger, you're going to spend less time at home. All right. You'll be like these electrons that in metallic bonding. All right. And stray. All right. And so when these electrons stray, it is recorded. It is recorded by the nucleus. That's why this diagram has so the nucleus, and then the nucleus then has a temporary positive charge, because remember, say the purpose of the electrons, one of the purpose of electrons in atoms is to balance the positive charge, all right, of the nucleus. The nucleus has protons which are positive, which are these red circles here. Red and black supposed to balance out each other. So if you have 10 red, then you must have 10 black, right? Or if you have 10 positive, you must have 10 negative. So these dots here are electrons which are negatively charged. It means that you will have 10 of these red positive. So when one electron leave now, it creates an imbalance now. All right. So the next sentence would say it leaving behind, all right, leaving behind the positive, or yeah, leaving behind the positively charged nucleus. All right, so that's pretty much what it does here. And so that's metallic bonding. All right. The positively charged nucleus is what they call a cation. All right. So there you go. But okay. Any questions here, guys?
No, sir.
All right. So, and again, we were supposed to describe ionic simple molecular and giant molecular crystals. We're supposed to do that. All right. So, copy that. Did you guys have devotion yesterday?
I did not see a link for devotion, so no, sir.
Okay. All right. So good. And that's metallic bond for you right there. All right. And so when stop here then, since it's about 9:20. All right, and we should be having physics class after this. But you heard the news about no school, right? Until April 13.
Yes, sir.
Okay. So it means that you guys should be looking to get some vaccine after April 13. Mm. All right. So get ready, Jonathan. Get ready, Kimberly. Um, hopefully Terika. Ready. Terika. Seem to be having internet problems though. All right. So this is it now, guys. So next class now, I think we're going to and I believe I would want to do some do another plan and design lab to bring up that number so that we can meet the deadline as soon as possible. All right. So next class all right, I'll let you know what that is. If I get the chance, I will send the outline for it in the group so you can look through it to see what the next plan and design lab would be. And then we'll take it from there. All right. Carry you guys up to 7 labs, and then you should think about carrying out one of them. So I'm going to have to find one that you guys can carry out. All right. Might even have to talk to Mr. name again, Mr. Miller. So see how that go. All right, guys. So if you don't have any questions, then I guess you guys can go. Jonathan and Terika would have physics class no, but Kimberly, you have what, IT now?
Yes, sir.
Okay.
Okay, bye, sir.
All right, bye, Kimberly. All right, so let's go to this.